Hello guys! Naka-order na ba ang lahat ng Simplified Reinforced Concrete Design by Engineer Mark Jefferson B. Castro? Kung hindi pa, you can message us directly sa messenger link na nasa video description. Meron rin silang Simplified Steel Design and Foundation Engineering. So yung ating Simplified Reinforced Concrete Design and Simplified Steel Design ay parehas na base sa NECP 2015 or National Structural Code of the Philippines. So ano pang hinihintay ninyo? Huwag nyo nang hintayin maubos ang kanilang stock at dun pa lamang kayo o-order. So ano guys? Nag-enjoy pa kayo sa ating discussion for Reinforced Concrete Design? I hope talagang nag-enjoy kayo at marami kayo natutunan sa mga discussion and also sa problem solving ng ating subject na to. Ngayon naman ay magdadako tayo sa ating chapter 3, which is the ultimate strength design or strength design method. So kung napansin nyo sa ating chapter 2, puro analysis lang ang ginawa natin sa singly and doubly reinforced beam. So dito sa ating chapter 3, ang gagawin na natin is analysis and design ng singly reinforced beam and doubly reinforced beam. Bakit yun ang aming ginawa? Kasi yung ating working stress design ay tinatawag na ngayon as alternative approach method. Kaya ang mas magiging focus natin sa reinforced concrete design dito sa 𝗕𝗵𝗽𝗁 ay USD o Ultimate Strength Design Method. Again, this is Engineer 𝗕𝗲𝗬𝗏 and you are watching 𝗕𝗵𝗽𝗁. Don't forget to subscribe and hit the bell icon for notifications and updates on our YouTube channel. So, wag na tayo magpatumpik-tumpik pa. Let's start on our Chapter 3 Ultimate Strength Design Method. Beams are structural members that are primarily subjected to flexure or bending. There are two philosophies of design that are used to analyze the beam section. Yun nga, yung ating chapter 2 which is working stress method, and number 2, ito sa ating chapter 3, strength design method. In the working stress method, a structural element is so designed that the stresses resulting from the actions of service loads or working loads and computed by the mechanics of elastic members do not exceed some pre-designated allowable values. Kaya nga tinawag siya as allowable stress design. Pero dito sa ating strength design method, formerly called as ultimate strength design or USD, the service loads are increased by factors to obtain the load at which failure is imminent, na kung saan ay diniscuss na namin under sa chapter 1. Itong pag-increase ng ating mga loadings by using factors. So these loads are called factored loads or factored service load. Kasi nga, under sa working stress design or method, hindi tayo nagdadagdag ng mga loadings, hindi ba? So dito sa ating strength design, since gumamit tayo ng factors, tatawagin natin yon as factored load or factored service load. The strength design method requires the conditions of static equilibrium and strain compatibility across the depth of the section to be satisfied. The cross-sectional dimensions of a flexural member and the required amount of flexural reinforcement at critical sections are determined using the strength and serviceability requirement of the code. For flexure, the design strength for at all sections shall satisfy VMN should be greater than or equivalent to our MU. So para mas maunawaan natin itong strength na to, gawin nating general. So paano yun? Siyempre, meron tayong beam. At yung beam na subject sa shear and also sa bending moment. So ibig sabihin, pwede nating i-test or i-check yung strength ng ating beam in terms of their failure. Meron tayong shear failure and meron din tayong flexural failure. Therefore, based on that failure, yun din yung magiging strength niya. Kaya meron tayong tinatawag na shear strength and flexural strength. Meron rin namang mga beams na nasubject sa torsion. Kaya pwede nating sabihin na torsional strength. Paano naman kaya kapag column? Kapag column, since ang ating column ay subjected to axial load which is perpendicular to the cross-sectional area of the column, therefore, ang column natin ay mag-fail in terms of compressive stress or axial load. Diba? Kaya, meron tayong tinatawag na axial strength for column. Kaya, yung mga strength na to ay hindi lamang Mn. Mn for bending, V sub n for shear, T sub n for torsional, and axial force usually is N, normal force. Kaya iba-iba yan. Kasi nasanay tayo kapag sinabi nating design strength is Mn. So, ibig sabihin, yung design strength na to ay para sa lahat ng type of structural members. Pwedeng column, pwedeng beam. Ngayon, yung strength na yun ay nagbabago-bago. Depende kung ano yung gusto nating kunin na strength. So, based on those failures, na kung saan ma-check natin or makukuha natin yung different strength ng kada structural members, makukuha natin yung tinatawag natin na strength sub n. Na kung saan yung sub n na yun, ang ibig sabihin ay nominal. Kaya, yung strength, kapag merong sub n, meaning that is the nominal strength. Meron tayong nominal moment, nominal shear, nominal torsion, and also nominal axial strength. So, ano nga bang ibig sabihin ng nominal? So, kapag sinabi natin nominal, ito yung, kumbaga, original strength ng ating beam. Kapag nag-create tayo or gumawa tayo ng isang beam, meron na kagad dyan strength, di ba? At yung strength na yun ay nakadepende sa strength ng concrete, strength ng bakal. Kagaya ng ginawa natin saan? Sa ating chapter 2 na kung saan kinuha natin yung moment capacity. Ibig sabihin, ang nakuha natin dun ay strength. Pero, yung strength na yun ay according dun sa design ng ating beam. At yung tinatawag natin na nominal strength under dito sa ating chapter 3, ultimate strength design. So kapag ang ating mga nominal strength ay minultiply natin ng reduction factor phi, ang tawag natin dun ay design strength. Ang ibig sabihin ng design strength is, kukunin natin yung percentage ng ating 100% nominal strength. For example, ang ating nominal flexural strength ay 100 kN. Then, imumultiply natin siya ng reduction factor. If you say reduction factor, it is equivalent or less than to 1.0. Meaning, kukuha tayo ng siguro 95%, 90%, 80%, 85%, 65%, 75%. Iba-iba yan, nag-vary yan sa iba't ibang type of structural member. So let's say, nakukunin natin is 90% ng 100 kN. O di ba, mas safe yun. Bakit? Kasi hindi naman talaga tayo sigurado na yung 100% na strength ng ating beam, which is 100 kN ay mag-work. So ina-assume natin na medyo hihina siguro yung ating beam. Possible na ang mag-work lamang ay 90% para dun sa beam. So, in that way, mas safe tayo. Kumbaga, mas binababa natin or kaya nga tinawag na reduction factor, mas nire-reduce natin yung strength ng ating structural member. Kumbaga, ang sasabihin ko sa iyo ay, ang kaya ko lamang buhatin ay 25 kg ng bigas. Pero, ang kaya ko palang buhatin ay 30 kg ng bigas. So, ibig sabihin, ang ibibigay nyo sa akin ay, it's either 25 kilos or mas mababa pa. E di mas safe ako kasi ang kaya ko pala talagang buhatin ay 30 kilo ng bigas. Ganun ang design strength. So, now, what is our MU? Ang sabi rito, ang MU is the moment due to the factored loads, which commonly is referred to as the factored design moment. So, medyo nakakalito siya, di ba? So, para hindi kayo malito, kapag design strength, ibig sabihin, imumultiply lang natin yung ating nominal strength ng reduction factor P. Then, paano naman yung MU? Experience ko kasi nung nagre-review ako sa board exam, nalilito ako sa mga terminologies and notation. Minsan kasi yung ating MU is tinatawag na ultimate moment capacity. So, bakit kaya siya naging ganon? So, kung napapansin ninyo, yung ating MU is less than or equivalent to our PMN or the design strength. So, ibig sabihin, kung ultimate moment capacity, ang mangyayari is, wala pa tayong applied loadings. Ang tanong kasi sa problem is, ano kaya yung ultimate moment na pwedeng i-carry ng ating beam? So, since ang ating MU ay based on the factored loads, at wala pa tayong mga loadings, ibig sabihin, kukunin natin yung ultimate moment capacity natin or ultimate moment na kikerry ng ating beam dun sa ating design strength. Kaya mangyayari, yung ating ultimate moment capacity is approximately equivalent to our design strength. So, ganun lang siya kasimple. Kapag design strength, kukunin natin siya sa nominal strength. Kapag naman ultimate moment capacity, kukunin natin siya sa design strength. At kung ano yung design strength natin, yun na yung ating magiging ultimate moment capacity at yun na yung magiging maximum moment na dadalhin ng ating beam.
3.2 Design Assumptions for Concrete.
It is under sa NACP 2015 Section 422.2.2. So the following are assumptions for the design method. Maximum strain at the extreme concrete compression fiber shall be assumed equal to 0.003. So i-note natin yan. Ang atin daw strain sa ating extreme concrete compression fiber is equivalent to 0.003. Yan. Number 2, tensile strength of concrete shall be neglected in flexural and axial strength calculations. Number 3, the relationship between the concrete compressive stress and strain shall be represented by a rectangular, trapezoidal, parabolic, or other shape that results in prediction of strength in substantial agreement with results of compressive tests. So ito kasi is anyway, madidiscuss natin ito kapag ando na tayo sa derivation ng mga formula or equations para sa analysis ng beam. Number 4, concrete stress of 0.85 𝗵𝗡𝗄 shall be assumed uniformly distributed over an equivalent compression zone bounded by edges of cross-section and aligned parallel to the neutral axis located at a distance alpha or A from the fiber of maximum compressive strain as calculated by alpha or A is equivalent to beta 1 multiplied by C. Na kung saan yung C is the position of the neutral axis with respect to the extreme concrete compression fiber. Tapos sabi niya rito, yung alpha daw is multiplied, ang ating alpha daw is equivalent to beta 1 multiplied by C. So ano tong 0.85 𝗵𝗡𝗄 na to? Imbis na 100% 𝗵𝗡𝗄 ang gagamitin natin sa analysis ng ating reinforced concrete beam, ang kukunin lamang natin ay 85% ng 𝗵𝗡𝗄. But anyway, ipapakita rin natin sa derivation ng ating mga equations. Then last, distance from the fiber of maximum compressive strength to the neutral axis, ito, yung C, shall be measured perpendicular to the neutral axis. So now, i-derive na natin yung mga equations para sa ating singly reinforced beam based dito sa design assumptions for concrete. So sabi rito, dun daw sa strain natin, yung ating maximum strain for extreme concrete compression fiber ay equivalent sa 0.003. So ito yun. Yan. Siyempre, linear pa rin tayo sa strain. So ito yung strain natin or maximum strain para sa concrete. At sabi ron ay equivalent daw yan sa 0.003. Ito naman yung strain natin para sa bakal. Tapos, ang sabi rito is, ayan, yung relationship between concrete compressive strength is pwedeng rectangular, trapezoidal, or parabolic.
So since ang ating ultimate strength design method is lagpas na ng proportional limit, ang magiging stress diagram na natin ay parabolic. So, kapag i-analyze natin yung singly reinforced beam sa ating parabolic stress distribution, ang tawag ron ay exact analysis. At kung exact analysis yan, mahirap yan i-analyze. So, in 1937, pinapose ni Whitney na i-replace yung ating stress distribution ng rectangular stress distribution, na kung saan nag-conduct ng maraming experimental testing na kung saan nakapag-come up sila ng 0.85 𝗵𝗡𝗄. So, ibig sabihin, hindi na natin gagamitin yung 100% 𝗵𝗡𝗄, kundi 85% na lang. At yung corresponding na depth ng compression zone ng ating 0.85 𝗵𝗡𝗄 is yung distance alpha or A, which is equivalent to beta 1 multiplied by C. At yung ating C is the distance or location of the neutral axis with respect to the extreme compression fiber.
So since lagpas na nga tayo sa proportional limit, ang mangyayari is, yung stress diagram natin ay hindi na linear. So paano kaya yun, sir? So ganito na yung itsura ng ating stress diagram. Yan. Tapos, ito na yung compressive force. Ito naman yung tension force. So, tawagin natin to as C. Ito naman is tension force T. So nakita nyo dito na hindi na linear yung ating stress diagram. Hindi ba? So medyo mahihirapan tayo. Yes. Ito yung distance C na. Ayan, yung neutral axis natin. Yan yung distance C. So same lang naman sa ating chapter 2. So nasaan yung ating F'C? This is our F'C. Yung maximum stress sa compression fiber. This is our F'C. So, kung yan ang F'C natin, ibig sabihin 100% F'C yan. Yun ang ibig niyang sabihin. So, sabi rito, ang kukunin lang doon natin ay 85% ng F'C. Tapos, ang gagawin natin is uniformly distributed daw yan over an equivalent compression zone bounded by the edges of the cross-section and aligned parallel to neutral axis. So, nasan ba yung saan yan? Cross-section natin sa compression zone. Ito yun, no? Ito yun. Pero, nasa distance A daw siya. So, i-zoom natin to para talagang mas malinawan kayo. So, check natin to. Sabi, dun sa ating Whitney stress block, mas maliit yung A. Yan. So, yun. So, ito yung ating distance A. Which is equivalent nga sa ating beta 1 multiplied by C. So, drawing natin yung ating rectangular stress distribution. Ito yun. Na kung saan, nakuha natin to mula sa 0.85 of F'C. So, nasaan kaya yun? Itong, ano na to, width na to. Oops, sorry. 0.85. So, this is our 0.85 of F'C. Tapos, sabi dun sa ating, provision, ito, concrete stress of 0.85 F'C should be assumed uniformly distributed over an equivalent compression zone bounded by edges of the cross-section and aligned parallel to the neutral axis located at a distance alpha or A. Okay, no? Sabi rito, itong 0.85 na to ay uniform daw. Uniform all throughout the distance alpha bounded by a distance A. Yan daw siya. Throughout niyan is 0.85 F'C. Kaya naging rectangular stress distribution siya. So, yun yung ating alpha or distance A. Tapos, kung makikita nyo, itong Whitney stress block is ito. Yan siya. So, siguro mas litan pa natin kasi sabi niya 0.85 of F'C. So, siguro pwede siyang ganyan. Yan. Litan natin. Ito, litan rin natin para magpantay sila. Okay? So, medyo mabagal lang. Ayan, yan siya. So, ito yung ating 0.85 F'C kung nakikita nyo. Yan. Ito yung ating 0.85 of F'C. Yung maliit na yan. Tapos ito, yung it's width, no? Itong width na to is F'C. So, ano nangyari? May sobra tayo rito, sir, oh. Tapos ito, saan napunta? So, kung napapansin nyo, merong space dito based on our actual parabolic stress curve na wala dun sa ating rectangular stress distribution. So, ito, para mapuno to, magagaling siya dito. Yan. Diyan siya ilalagay. So, hindi lang talaga eksakto yung drawing natin, no? So, pero ganun yung concept niya. Itong 0.85 F'C na to multiplied by alpha A is also equivalent sa area ng ating actual stress or actual parabolic stress distribution na to. Okay? Ginawa lang natin siyang kumbaga, simplified. Okay? Kasi kapag, gaya nga na sinabi ko kanina, kapag ginamit natin yung ating parabolic stress distribution, mahirap yun at yun yung tinatawag na exact analysis. So kung exact analysis ito, ano naman ang tawag dito? Ang tawag dito is approximate analysis. So wala namang problema sa approximate analysis no? Kasi ang ibig sabihin lang naman ng approximate analysis is hindi talaga tayo 100% sure. Hanggat kaya, medyo malapit sa 100% pero hindi talaga tayo sigurado na makukuha talaga natin yung 100% accuracy ng ating mga analysis. Halos lahat naman ng mga concept na inaaral natin talaga is approximate. Okay? So, ano naman ang tulong nung Whitney stress block? So, ito na yung ating compressive force C. Ito naman yung ating tension force T. So, ang tulong nito is mas mapapadali nating isolve yung ating moment capacity. Bakit? Siyempre, yung ating C and T is couple force. Kaya magkakaroon tayo ng couple moment or bending moment. Na kung saan, ang bending moment natin is equivalent to what? C multiplied by what? By moment arm. So, ang tanong is, ano yung moment arm natin? Ang moment arm natin is, ito, yung ating effective depth, D, then, minus yung Y bar. Ano naman yung ating Y bar? Yung Y bar natin is equivalent to A over 2. So, para tinasabing A over 2, nasabi natin na A over 2 kasi rectangle lang naman to. Diba? So, gamit yung ating approximate analysis, mas napadali yung pagkuha ng ating moment capacity or mas napadali yung pagkuha ng ating moment arm. Ang ating moment arm is equivalent to T minus A over 2. Imagine kung gagamitin pa natin yung ating parabolic stress distribution, hindi natin alam kung nasaan eksakto yung location ng ating compressive force. Kaya ito yung gagamitin natin, yung Whitney stress block. So mula rito ay makakapag come up na tayo ng mga equation. So mula rito, by summation of forces horizontal, ang ating C and T is equal. Na kung saan ang ating C or compressive force is equivalent sa area nito. Ang area niyan is 0.85 prime C, then yung height niya is yung A. Then, ang area naman nito is B. Ayun, yun pala, B. Yan. Okay? Then, yung ating namang T is equivalent to AS FS. Kaya, kung kukunin natin yung ating A, makukuha natin yun by equating yung equation ng C sa T. So, this is 0.85 of F prime C multiplied by A multiplied by B, then equivalent to AS multiplied by FS. So, ito hindi nyo naman kailangang i-memorize Basta alam nyo yung concept ng equilibrium condition na kung saan ang C is equivalent to T. So, ito yung i-memorize natin. Ang C is equivalent to 0.85 F prime C of A multiplied by B. Then, ang ating T is AS FS. So, ano naman yung ating moment? Ating moment is equivalent to, or kaya ang gawin natin dito is, since under tayo ng ultimate strength design or strength design method, ang gawin natin is, ito ay MN or nominal moment. So, ang ating nominal moment is equivalent to C multiplied by T minus A over 2, or kaya ang ating MN is equivalent to T multiplied by D minus A over 2. Tapos kung pinapahanap naman sa problem is yung location ng ating neutral axis from the extreme compression fiber, ang ating C is equivalent to A over beta 1. So ano naman ang value ng ating beta 1? So andito siya sa ating NCP 422 or section 422.2.2.4.3. The values of beta 1 shall be in accordance with table 422.2.2.4.3. Okay? Yan. So, ito yung gagamitin natin. Actually, tatlo siya di ba? Kapag daw ang ating F prime C ay greater than 17, but less than or equivalent to 28 megapascal, ang ating beta 1 is 0.85. Then, kapag naman ang ating F'C ay greater than 28 but less than 55 megapascal, ang ating beta 1 is equivalent to 0.85 minus 0.05 multiplied by F'C minus 28 over 7. Kapag naman ang ating F'C ay greater than or equivalent to 55, ang ating beta 1 ay 0.65. So take note ang ating beta 1 ay should be greater than or equivalent to 0.65. Hindi tayo pwedeng bumaba sa 0.65. Kung sakaling ang nakuha natin dito na beta 1 is mas mababa sa 0.65, therefore, ang kukunin natin ay 0.65. So ito, may nakalagay na change equation. So ibig sabihin nito is hindi kasi ako sanay na isulat yung equation ng beta 1 sa ganitong format. So, ganito kasi yung mas kinasanayan ko na beta 1. So, beta 1 is equivalent to 0.85 minus 0.05 over 7 multiplied by F'C minus 28 megapascal. So, mas sanay ako sa format na to. But anyway, pares lang naman pares lang naman siya, di ba? Mas sanay lang talaga ako dito pag minememorize. Tapos, sa NCP 2010 and 2001 ata, ito is 30 megapascal, no? Iba siya. So, ito, since under tayo ng NCP 2015, this is 28. So, lagi niyong alalahanin yan, no? Kapag 2010 or 2001, 30 megapascal. Pero kapag 2015, then this is 20. And also, sa analysis ng singly reinforced beam, itong Fs na to ay nagbabago. Depende yan sa makukuha natin na value ng Fs. Kapag ang ating Fs is greater than our Fy, therefore, ang ating Fs is equivalent to Fy. Pero kapag ang ating Fs is less than, ito pala greater than or equivalent yan. So, kapag ang ating Fs is less than sa ating Fy, therefore, ang ating Fs is makukuha natin mula rito sa equation na to. Ang ating Fs is equivalent to 600 multiplied by D minus C over C. So, saan kaya galing itong equation na to? Makukuha natin itong equation na to sa strain diagram. Dito. Okay? So, ano ba yung equation ng ating strain based on our learning sa strength of materials? Ang ating strain is equivalent to F over modulus of elasticity. So, kung ito ay strain ng bakal, so therefore, this is equivalent to Fs over Es. Na kung saan ang ating Es or modulus of elasticity ng steel is equivalent to 200 gigapascal pala. Ayan. Or 200 times 10 raised to 3 megapascal. Tapos sa concrete naman, ano ba yung sa concrete? Equivalent sa 0.003. So mula sa ating strain diagram, pwede tayong mag-ratio and proportion. So, 0.003 over distance C, then equivalent to strain ng bakal, which is equivalent to Fs over 200. So, sa baba yan, no? Fs over 200,000 megapascal, then over distance, nag-distance na to, which is D minus C. So, cross-multiply natin, ang matitira is what? Fs is equivalent to what? 200,000 multiplied by 0.003, dun nanggaling yung 600. No? So, 600. Tapos, ang nasa taas is D minus C. Tapos, nasa baba is yung C. So, dun nanggaling yung Fs. Kaya, sa solution natin ng una, pwede natin i-assume na mag-yield muna yung bakal. So, ibig sabihin, kung mag-yield ang bakal, papalitan natin yung Fs na to into Fy. Yung Fy natin is yung given na yield strength ng bakal. Tapos, once na nakuha na natin yung A, then makukuha na natin yung C, di ba? Then makukuha natin yung Fs. Saka natin i-check kung siya ay greater than Fy or less than sa Fy para malaman natin kung ano ba talaga yung mag-govern na strength ng bakal. So, anong ibig sabihin kapag nag-greater than or equivalent sa Fy yung ating bakal? Ibig sabihin nag-yield or bumibigay na yung bakal. Pero kapag naman less than yung ating Fs do sa ating Fy, hindi pa siya nag-yield or hindi pa niya nare-reach yung maximum yield strength yung maximum yield strength nung bakal. So ito medyo madali lang naman yan kapag nasa ano na tayo, problem solving.